final example as to how we can try to approximate the change of a function, we're going to go ahead and take a look at this change in the lateral surface area of a right circular cone, and it has a height of 6 meters, and the radius decreases from 9 to 8.9 meters. And we're going to use this formula. The surface area is going to be equal to pi r times the square root of r squared plus h squared. So the derivative for this isn't too bad, but we are going to have to utilize a product rule when we're doing this, as well as a chain rule. All right, so we know that the height is 6 meters. So let's just plug that in right away. We also know that delta r is going to be terminal, which is 8.9 minus 9. So that's negative 0.01. All right, and so what was going to happen is that the surface area should be decreasing, all right, which makes sense because if we have a negative, that means it's changing that way. So our S is going to be equal to our pi r, and let's just make this r squared plus 36 to the 1/2 power. All right, and again, what I did was I just plugged 6 back in for h right there. So that way we can go ahead and find the derivative for this really quickly. All right. To be able to find the derivative, we need a product rule. All right. So if we're using the f prime g plus fg prime mentality, then let's call little f pi r, and let's call little g r squared plus 36 to the 1/2. Now, f prime is pretty easy to find. That's just going to be pi. And then for g prime, we're going to have to use our chain rule. All right, so this is going to be 1/2 r squared plus 36 to the minus 1/2. But then we need to multiply by the derivative of this interior function. And the derivative of r squared is going to be 2r. These 2's and the 1/2 are going to cancel each other out. We can move this to the denominator. And so another way to write g prime is going to be r over the square root of r squared plus 36. At this point, we can go ahead and use our f prime g and fg prime formula, but we can't forget that we're finding a differential. So we are going to, at some point, have to plug in our r prime for this, or I'm sorry, our dr for this. All right. So I'm going to call this s prime, and that's going to give us our f prime g. So that's pi square root of r squared plus 36. And then we have our fg prime. All right, so that's going to be plus pi r, and then times this animal right here, this r times over square root of r squared plus 36. Right, so I'll just erase that just so we have room. That's going to be times r over the square root of r squared plus 36. And we can't forget that we're going to multiply all of this by dr. All right. Now, at this point, we are going to substitute 9 back in for our r. All right. So if we do that, that's going to give us pi times the square root of 81 plus 36 plus pi times 9 over the square root of 9 squared, which is 81 plus 36. And we'll clean this up in a moment. We know our dr all the way back up here. Remember, we got that delta r, which is going to be dr is negative 0.01. All right. So we're going to have to compute this a little bit further down. All right, just in case it says for us to give an exact value. All right, so let's compute a little bit further and see if we can get to something that makes a little bit of sense. So we know that 81 and 36 is going to give us 117. So we're going to end up with pi roots of 117 plus 81 pi over the square root of 117. And that's going to be times negative 0.01. All right. Now, 0.1 or 117, I believe, has a factor of 9 in it. so we can actually factor this down a little bit. And then we're going to get a composite answer for this. So 117 divided by 9, and that's going to give us 13. So another way to write square root of 117 is going to be the square root of 9 times 13, or 3 roots of 13. All right, so we could simplify that just a little bit more just by using our good old algebra 2. And so we rewrite this as quantity 3 pi root 13 plus 81 pi over 3 root 13. And we still have that negative 0.01. All right, we might have to erase a little bit here because we're almost out of room. We're going to get a common denominator, or actually we can simplify this because this is just going to become 27 pi. Right, so we're going to simplify this because we have the 3 and the 81, they simplify. This will just be a 27. And so we just need to get a common denominator, the square root of 13. So I'm going to erase some stuff really quickly so we have some room. So hang tight if you want to fast forward just a little bit till we clear out all this stuff. Or if you just want to watch me fumble through the erasing stuff, that's fine too. All right, so I'm going to get a common denominator. And what I'm going to do is I'm going to multiply this by root 13 over root 13 to get the common denominator. So we're going to end up with 3 pi root 13 times root 13 over root 13. All right, so I just multiplied this by root 13 over root 13 to get a common denominator, plus 27 pi over root 13. Now we're still multiplying that by negative 0.01. All right, so I haven't forgot about that. We know that this just turns into 13 when we multiply two radicals together of the exact same radical. And then we have 13 times 3, which is going to give us 39. All right, so this whole thing right here, that's just going to turn into 39 pi. And now we can just add these together because we have a common denominator. So we know 39 and 27, that's going to wind up being 66. So we end up with 66 pi over root 13 times negative 0.01. All right. And certainly we could multiply the 66 times pi. And so the most exact answer I think we can get for this is going to be negative 0.66 pi over the square root of 13. All right. And I'm sure we could throw that into our calculator and get some sort of approximation. All right. So make sure we can do that as well. And so that's how we can try to utilize our differentials to be able to approximate what's going to be the change in some sort of geometry with respect to our differentials. All right, so that's all for this section. And the next section, we're going to take a look at, I believe, some more with L'Hopital's rule and then some other sorts of applications of our derivatives.